Uh, in the 20s, I believe.
Never in my life have I been more disappointed to be above average.
It was like a bunch of the definition of
19 out of 25.
All right. What I want to do is start by recapping some important some of the important ideas that we came up with last time.
Last episode.
So a recap. Directional derivative. The directional derivative gives us the rate of change of, I'm going to say z equals f of xy in the direction of an arbitrary unit vector. So that was one of our big ideas from last time, was the directional derivative. We came up with a process for calculating the directional derivative, and we used an argument that was based on, essentially we're parameterizing our vector in terms of its arc length. Our second major idea was the del operator. So our del operator, del, is defined as, it is a vector. In your book, you'll see del with a bold notation showing it's a vector, but it is a vector, so you should notate it as a vector. Defined as these partial derivatives, d dx, d dy, and if we can keep going. We can make it as many variables as we want. We'll just use 3. It must operate on something to have meaning. So by itself, it doesn't have any meaning. It has to operate on something. For now, we're just going to operate on a function. In chapter 15, we'll talk about taking the dot product of del with a vector, or the cross product of our operator with a vector, and that will give us some other information about these vector things that we're talking about. The gradient, we use this notation to give us the gradient. Gradient functions turn out to will be very important in chapter 15 as well. So the idea of a gradient is one of the key ideas in multivariable calculus. Gradient of z equals f of xy is del f. And then we get the partial of f with respect to x, partial of f with respect to y as a vector. You'll also see the notation this is a little older notation as grad f. Or grad is just short for gradient. And there's a pretty well-known book about multivariable calculus called Div Grad Curl. And that has to do with the divergence, the gradient, and the curl. We'll talk about divergence. We'll talk about divergence in chapter 15. if we have our unit vector AB, then the directional derivative in the direction of u is del f dot u. And this is df dx a plus df dy times b. So we can use a gradient to easily calculate the directional derivative of a function. Del f gives the direction of maximum rate of change in f. So points in the direction of the steepest route up the hill. And the magnitude of del f at a particular point gives the magnitude of the maximum rate of change. So those were the kind of distilling down what we talked about last time into some bullet points. All right, it turns out that the gradient of our function gives us more additional information other than just the maximum direction of maximum rate of change and a way to calculate the gradient. And this additional information is what we're going to, one of the primary ways that we're going to use a gradient of a function. Directional derivative is important, but these other properties are going to be probably a little more important. All right, so we good with this information? All right, another important property. Another important property of the gradient, del f. So what I want to do is I'm going to draw a portion of a level curve. So in the plane, our level curves are in the plane. And I'll do that in blue. So we have something like this. So, portion of a level curve. So on this level curve, z is a constant. Now I'm going to, at this point, right here, I'm going to draw a unit tangent vector. So let me draw that in green. Let me do a little better unit tangent vector. There we go. So I'm going to call that green vector u. And u is a unit tangent vector. So if that's a unit tangent vector along the level curve, what is the directional derivative at that point? 0. Directional derivative of f equals 0 because z is constant. Well, that tells us that del f dot u equals 0. Because that's how we calculate the directional derivative. Well, what does that tell us? The gradient and this unit vector are orthogonal. So del F is orthogonal to that unit tangent vector. Well, that means that del F is normal to the level curve. So if I draw the gradient vector, I'll draw that in red, there would be del F. Yes.
Always point outside the curve.
I drew it this way. It would technically it would depend on if the level curves were, if the constant were larger this way or that way. So it depends on which way the surface is rising, because it's going to point in the direction of maximum increase. So for this one, we visualize we're going uphill as we go up that surface. If it were the other way, it could point the other way. And this is an arbitrary function, an arbitrary level curve at an arbitrary point. So this is going to be true in general. So we're going to say, in general, we're going to say f is differentiable. We have a nice function. And we're going to say that del f at a particular point is not 0, because we know if the gradient is 0, then any directional derivative is 0. Then del f at a particular point is normal to a level curve through that particular point. So this is our second, I guess our second important property of the gradient, is gradient is normal to level curves. Now, what we're going to do on Thursday is talk about a surface and how we can find a normal vector to a surface using the gradient. So the gradient as a normal vector is going to be an important one, probably the most important application that we'll use the gradient for. All right, so this eventually we're getting close to my favorite example of this part of the chapter. So our gradient is normal to level curves. All right, so let's look at a quick example. Of how we might apply this. Let's say we're asked to find a unit normal vector to the graph of 3x squared minus 2y squared equals 1. So let's think about how we would have done this in chapter 12. So in chapter 12, we could parameterize the curve, right? Find the unit tangent vector, r prime, or the magnitude of r prime. And then we can use that unit tangent vector to find the unit normal vector at that particular point. So there's a little bit of work involved there. And I'm going to say this is at a particular point, 1, 1. So this gives us a slightly different way to do that problem. We can think of this as 3x squared minus 2y squared equals 1 is a level curve of z equals 3x squared minus 2y squared. That's a level curve where the constant is 1. So what's going to give us a normal vector to that curve? Del f gives us a normal vector. Because we know that del f is normal to that level curve. So del f, when we find the gradient, del f is nice easy derivative, 6x I hat minus 4y j hat. And at 1, 1, del f 1, 1 is 6i hat minus 4j hat. So that's a normal vector. We want a unit normal vector. So what would we do? Yeah, we want to normalize this. So we want to normalize it for a unit vector. So our unit normal is it 52? 36 plus 16? 52. 1 over the square root of 52 times 6 negative 4. What is this curve? 3x squared minus 2y squared equals 1. That's a hyperbola. So what we have here, if we sketched a quick graph, here's a hyperbola. And at 1, what we did was we calculated this unit normal vector here. Little easier than the process of parameterizing this and finding our unit tangent vector. Parabola, hyperbola, how would we parameterize a hyperbola? Where we have something like 3x squared minus 2y squared equals 1. Probably secants and tangents, right? Secant squared, tangent squared minus secant squared is 1, something like that. Secant squared minus tangent squared is 1. So when you have a minus sign, you're probably going to parameterize in terms of secants and tangents of theta. So that would be your parameterization.
Is the point supposed to be on 1, 1, or is the end of the unit vector?
This is at 1, 1. There's 1. Not drawn to scale.
Yeah.
Right. All right. My favorite example of the first 6 sections of chapter 13. Yes, but it's not as fun as this one.
So wait,
I guess you could say this is your favorite of all.
so this is your favorite of the whole chapter then?
I think so. Of chapter 15. All right. T of xy is 100 minus x squared minus y squared. And this is the temperature field. So this tells us the temperature at any point on a metal plate. So you've set up this metal plate, you've measured the temperature, and you've decided this function describes the temperature at any point on that plate. We want to find the path of a heat-seeking particle placed at 4,3. So we have this particle. I guess we could think of this as a temperature in a place of area of two-dimensional space, and you have some kind of device that goes towards the highest temperature, a heat-seeking missile or some kind. As a bonus question on a test once, I asked students for a bonus what a heat-seeking particle would be, and one student asked a cat in a snowstorm. That was a heat-seeking particle.
Did you give them the points?
Yeah, definitely. I thought that was a good example. All right. Well, this is all we have. Well, what's one thing that we know points in the direction of maximum temperature? The gradient. Del T points in the direction of maximum increase of T. So at any point, this particle is going to move in the direction of del T. So let's calculate our gradient. Del T is minus 2x I hat minus 4y j hat. All right, so the path means, is it 4? Not 4? 2? Oh, I want a 2 here. Well, and when it says find the path, that means an equation like y equals some kind of equation for the curve that this particle travels on. So let's call the path that it moves along is some x of t I hat plus y of t j hat. So that's the path it moves at any particular time. And I'm going to call that r of t. So that's the path as a function of time. We place the particle on the plate, and in time it moves along this path. Well, if that's our path, what is another vector that points in the direction that we're moving? For a vector value function. What? The tangent, a tangent vector. What gives us a tangent vector to this curve? R prime points in the direction of motion. Also. So R prime also points in the direction of motion. Well, if del t and r prime are both pointing in the same direction, what can we say about them?
They're probably equal.
Not that they're equal, they're parallel. Del t and r prime are parallel. They're the next best thing to being equal. What can we say about parallel vectors? They're scalar multiples.
We were just ahead of us. Yeah, we were just we're just on a higher plane of existence.
They are scalar multiples. So I can say that del t equals, I'm going to say, I'm going to multiply by my constant here. C times del t equals r prime. So I can say C times minus 2x I hat minus 4y j hat. And I'm going to write r prime as dx dt I hat plus dy dt j hat. That's my velocity vector. Well, let's equate components. Since these are the same, we're going to equate components. Yeah, now we're going to set things equal to each other. So I'm going to say, I'm going to change my mind. I'm going to put this here. You could, if you have a C there, you could just change this to C1. Doesn't matter which side we multiply our constant on. I just like the way it sets up better this way. So we're going to say C dx dt equals minus 2x, and C dy dt equals minus 4y. What can I do here to get some kind of relationship between x and y? Can't I solve each of these for dt? And then set them equal to each other? So I'm going to say C dx over minus 2x equals dt, and that equals C times dy over minus 4y. And I can say that 2 dx over x equals dy over y. Multiply both sides by negative 4. Well, now what can I do? I can integrate. This is a separable differential equation.
Right.
I can integrate. I have all the x's on one side, all the y's on the other side. And I get the 2 natural log x equals natural log y plus my constant of integration. And what do I do here? I don't like those natural logs. Raise both e to the x to both sides. Write this in exponential form. So I get x squared, because I can write this as 2 natural log x is natural log of x squared, equals c2 y, because this is e to the natural log y plus c1, so that's e to the c1 times e to the natural log y. So my constant turns into a multiple. We multiplied both sides by 4, and that's why we only had a factor of 2. All right, so we have this constant here. Now we have initial conditions. We start at 4, 3. So we can plug that in, and we get that C2 equals 16/3. I just plug in 4 and 3 and solve for C2. And then I can write my equation as y equals 3/16 x squared. All right, so let's draw a picture here. What are these? If we draw level curves of this temperature, what are those level curves? Ellipses. So if we draw a picture here of our temperature at any particular point, we get ellipses like so. This is just a rough sketch of my temperature field. They're horizontal. Let me make that ellipse a little better. Kind of got. There we go. And our gradient is perpendicular, normal to these level curves at any point. So if our particle is moving like so, it's going to go perpendicular to that like so, perpendicular to that one, perpendicular to that one, perpendicular to that one, perpendicular to that one. And we get a nice parabolic shape there.
So if it's a line, the level curves are circles.
If it's a line, the level curves would be circles, yeah. The heat-seeking particle would move in a straight line. So that would be the path of that particle on that plate, if it starts at that particular point.
Yeah, absolutely.
And I would, based on what I saw in the quiz, make sure you understand what makes the axis of a ellipse horizontal versus vertical. That was.
Hey, idiots.
Yeah, and the difference between a definition of differentiability and a limit, that one was. We like that. Someone had the definition of differentiability at the beginning of class, and everybody wanted to use that for everything. That was an interesting. All right, questions. I love this example. It combines so many different things that we've done. We've got the gradient, we've got the unit tangent, we've got a tangent vector, we've got an r prime in the direction of motion. We've got some algebra, we've got differential equations, a couple of integrals. Mm-hmm.
We got kitty cats.
Right.
Yeah.
Yes.
What's that?
Is it gonna be on the test?
Well, I said this is my favorite example. That's kind of code word. All right.
Make sure we know what heat-seeking particles do. What else would be like? Aren't there like some metals that do that?
Yeah. I'm not gonna be here.
I they yeah.
A fly to light.
A fly to light.
But that's not heat. That's not heat. That's
Heavy.
light.
Yeah.
But could you use
It's-
an example of like something that just moves towards
Light
it?
Like sand.
Well, light is heat, but it's not. It's not.
But light is weight.
It's not.
Light is not